Okay, good evening, everybody, and welcome to BrisScience for June 2021. I'm Joel Gilmore, your host for this evening, and this is BrisScience, Brisbane's free public lecture series on science presented by the University of Queensland. And we aim to bring not just the best scientists, but also the best communicators to share their research with Brisbane and the rest of the world. We are online tonight, live streaming over Zoom, but I'm very excited to announce that this will be our last online talk before we head back to our wonderful home at The Edge at the State Library of Queensland. So more details on that at the end of tonight, so stick around. I'd like to start tonight by acknowledging the traditional owners of the many lands on which we're meeting tonight and pay my respect to elders both past and present. Also want to acknowledge the ongoing efforts of Aboriginal and Torres Strait Islander leaders to protect and promote Indigenous culture, to leave a lasting legacy for future leaders, elders, and the community. So tonight we are on Zoom and we will be taking questions after the talk. That means you can use the Q&A function at the bottom of your screen to ask questions, and we will go through as many of them as we can at the end of the talk. If you've got any questions or technical concerns for us organisers, you can use the chat function. But if you've got questions for our panellists we'll introduce in just a moment, please use the Q&A. Okay, that is all of our housekeeping. So it's my great pleasure to introduce our speaker tonight, Dr. Anita Parbhakar-Fox, who is a leading expert on mine waste, the stuff left over after we mine the coal or the minerals that we need. And she is the leader of the Mine Waste Transformation through Characterisation group at the University of Queensland's Sustainable Minerals Institute. She has more than 15 years experience in the industry, and so is the perfect person to talk to us tonight about what we do with and maybe even benefit from all those tons of waste. So to help set us on the path to a circular economy, please give a warm virtual welcome to Dr. Anita Parbhakar-Fox.
Thanks very much for the introduction. I'm just going to share my screen and hope that I do it right. Can we all see the screen, Joel?
That's perfect.
Excellent, great. Well, so thank you very much for having me here today. And as Joel said, I'd just like to also acknowledge the traditional owners and the custodianship of the lands on which we meet today. So without further ado, I just want to get straight into it. So tonight my talk is called The War on Mine Waste, and I guess this is a talk that I've been thinking about giving for a number of years, and it was, I guess, in many ways inspired by Craig Rucastle and his journey on the war on waste, which began in 2017. And I know that this somewhat span out of an idea that came out of the UK through the BBC with Hugh Fearnley-Whittinstall having a look at, coffee cup waste and plastic waste and food waste, etc. But what Craig did in 2017 was he put a spotlight on waste in Australia, and there are many different waste streams that Craig talked about in his project. So I just wanted to go through some of the wastes that he talked about, and I wanted to talk about the scale of the problem of waste. So if we start with something like plastic waste, for example, if you go through the archives and you have a look at how much plastic waste is produced, that's about 300 million tonnes annually. And if we think about what that means, it means that 5 trillion single-use plastic bags are used worldwide every year. So in total, about half of all plastic produced is designed to be used only once and then thrown away. And obviously the conversation around plastic waste and recycling has really taken off in Australia, which is great to see. And then we move on to things like food waste. So that was one thing that both Hugh and Craig focused on. And if we think about food waste, we produce, 1.3 billion tonnes of waste annually. And so that costs the global economy close to 940 billion tonnes a year. So that's quite a staggering amount in terms of costs to deal with food waste. I read a fact today that it said that throwing one burger away wastes the same amount of water as a 90-minute shower. So next time your kids are playing up at dinner time, you might want to remind them of that, because that's quite important when we think also about the pressure that we put on our water resources. And one of the other things that they focused on was textiles waste. So this is a bit harder in terms of finding a statistic, but 31 kilos per person is wasted annually from textile waste. And most of that actually ends up in landfills. So while some of us are quite diligent in terms of taking our unwanted goods to the charity shops and the salvos and so forth, so, perhaps they can have a second life somewhere else, actually the majority ends up in landfill, which I found quite surprising. In terms of furniture, that was another focus of Craig's. He looked at sort of fast furniture. Again, this is a bit of a tricky one to find some really decent stats, but just in America alone, last year, 12.2 million tons of furniture waste was disposed of. And, with the changes of how we work under COVID times, we certainly saw that a lot of people upgraded their furniture. So there was even more waste produced in that space last year. And then if we think about something like e-waste, now this is quite shocking. We all know that we are desperately wanting the next big thing in terms of our laptops, our phones, in the future, even our vehicles. And, in terms of e-waste, 50 million tons are produced a year. And this is actually equivalent to throwing out 1,000 laptops every single second, which is, again, it's astonishing to think of the waste footprint that we have in all of these different sectors. But there's one sector that Craig didn't touch on, and it's one very important sector, and that's the sector of mine waste. And actually, when you look through the statistics and you try and find an actual number of how much mine waste we produce a year, now in 2019, it was reported that we produce 100 billion tons per annum. And if you're finding that really hard to visualize, because that is quite an astonishing number and it is hard to visualize, then quite recently, Visual Capitalists, they took data from a paper that Daniel Franks here at UQ published, and they contextualized that. So what you can see here is, the city of Manhattan, and you can see that in terms of the global tailings, and that's one of the waste streams that mining produces, it's equivalent to 6 kilometers in height, 6 kilometers in width. That is a staggering amount of mine waste that we produce. And as I said, this is just for tailings. In terms of mining, we produce things like this. Oh, this is a waste rock, and there are many waste rock dumps around on the surface of the earth. I'm sure many of you pass them on long drives and visits to other places in the planet. But we also produce other things such as these. These are pyrometallurgical waste. This is a piece of slag. And obviously mine tailings, which I'm sure everyone's heard a lot about because of some of the recent big disasters we've seen happening in places like Brazil. And I'll touch upon that a little bit later on. So just to give you an essence of the scale, that's what we're dealing with. But the solution to this big problem of mine waste, it's not simply not to mine. And, you will see protesters and groups who, they very much state very strongly and passionately that we must stop mining. There should be no mining. But the thing is, it's really hard to make that argument stick because we just need mining. We cannot get away from the fact that for everything that we do, from transport infrastructure to, our satellites and our communications, right through to dealing with the COVID crisis, we need materials, we need those metals to actually fundamentally help the world function in the way that it does. So the idea isn't not to have mining, it's to mine smarter and to be better with how we deal with those waste materials. But here's the challenge. I mean, many of you, if you work in mining or the resources sector, you would have seen something like this already. But here's the challenge, I said that we need to mine smarter and we need mining so desperately. But the problem is that as time's evolved, across many commodities, we've already found the big deposits. It was really easy to go around, the explorers back in the heyday, they could just kick a rock or find something that looked a bit rusty like this. And, they knew that that was a sniff of an ore deposit. They knew there was a big one under there. So what they could do is they could mine that easily, simply, quickly. But as time's progressed and we've taken those really good deposits that are sort of a bit more shallow in the crust, what we're finding is that the ore grades across all these commodities, they're declining. So it's becoming harder to, meet the needs that we have, which means if we've got declining ore grades, we have to mine larger volumes to meet the needs that we've got. And the upshot of that is really that we're producing more waste. And again, if we're looking at this across a few different commodities, we can see that drastically in the last, over my lifetime, so I was born in 83, you can see dramatically, the amount of mine waste that we've produced is increasing. And unfortunately, and this is a statistic from 2008, unfortunately, this is set to rise when we think about some of the changes in our appetites for products. So what we're looking at here is an electric vehicle. And it is so exciting to be living through this point in time where we're thinking about changing our vehicles. I've been to places like Santiago, and as you can see, I'm Indian in origin, and air pollution is such a big deal impacting life. perhaps if we do change away from petrol vehicles and into electric vehicles, we've got that opportunity to actually, you know, deal with one of the problems we face environmentally. But the upshot of that is that we're going to need to mine more. So if we think about copper resources that we need, you know, that's going to increase. I mean, here, this is a really nice graph to show kind of the demand of copper that we need for electric vehicles. And when we've got countries like India saying that, you know, by 2030, they're going to be 100% in terms of electric vehicles, we can see that this contribution to global tailings from the copper industry alone is going to increase dramatically. So what are we going to do? And, you know, I was talking to someone at a mining company just last week, one of the major mining companies, and they said something which really stuck with me. And they said that mine waste is where CO2 emissions were 5 years ago in terms of global importance. So I guess it was really good to hear someone in a major mining company at quite a senior level actually recognize that, you know, dealing with mine waste is such a big issue, and it's only, you know, it's only going to come to the fore in terms of this global conversation. So it's great to be having this conversation with you right now and talk about some of the ways, I hope, providing we get there, some of the ways in which we could do things a bit better to meet our modern day needs, as well as be a bit smarter with how we reuse our waste. So I've talked a little bit about, you know, what I see as sort of one of the major challenges in terms of volume, but how do we actually deal with our mine waste currently? And many of you are probably thinking about that already. So waste rock and slag, they're normally engineered and placed into, you know, piles and dumps. And, you know, today, modern mines, they will characterize their waste rock and their future waste materials by sort of, I guess, industry standard practices. And they will design their waste rock dumps in such a way that they minimize environmental harm. And perhaps one of the big things that they're always looking out for is how to engineer it so they reduce the possibility of producing acid and metalliferous drainage. And we'll get to that in a little while. Tailings are, you know, in modern day practice, they're deposited into purpose-built facilities like these that you can see here around the Kalgoorlie mine in WA. You know, or in terms of waters and processed waters that are produced on site, one way in which you can do that is you can filter those, and then you can reuse that water on site. So, you know, spent water is one waste stream that we have to think about on a mine site. And in places like South America, it's really important to think about water management in mining because, you know, obviously the climate there is such that, you know, water is a really precious resource. So we have to really think about ways in which we can recycle our waters on site. Sometimes when we're trying to neutralise some of our other waste streams, like our tailings, for example, what we can end up producing are sludges. And sludges are perhaps one of the most tricky things to manage on a site because they need special handling and disposal methods. They can be really caustic, they can have really odd pHs and odd chemistries, and they can, you know, it can be very hard to actually get the water to separate from the solids in those particular phases. So they are a tricky one to deal with. Or we can simply reuse some of the materials. So if we've got gang material or material that doesn't have any of the metal value that we're chasing, if we can prove that these materials are inert, we can actually use them on site as construction materials. So what you're looking at here is a dam wall made of waste rock materials. Now, actually, in this particular instance, this dam wall was actually full of gold. In fact, when they built this wall, that they hadn't characterized their waste materials appropriately. And that's actually, I'm not going to tell you where it is, by the way, but it is actually quite well endowed in gold. So if it hadn't have been, then, you know, potentially that waste material could have been used really nicely for that dam wall. So you can see that there are sort of traditional ways to manage mine waste. There's industry standard practices. But the question I'm going to pose to you is this working? And we're going to revisit this a bit later on, but we have to really think about it. Is it working? I just want you to in the background while I'm talking, I just want you to think about times when you've seen mine waste, when you've been on your travels within Australia, internationally. You've probably passed things that look like these bizarre structures. And you think to yourself, you know, when you go back through your mind maps, do you think it's working? And I'm not going to tell you what my answer is, but I'm just going to leave that with you right now. Now, is it working? Now, there's two things that can happen, I think, two main impacts that mine waste can have if it's not managed properly. These can be chemical. So there's chemical impacts and there's geostability issues or physical impacts. So what you're looking at here is chemical. And so what we have here is quite often in these waste rock repositories or dumps or storage facilities, whatever, we often have this mineral here, and this is pyrite, okay? You can probably see it in this big chunk here. It's the darker looking stuff in this waste rock particle. And the thing is with pyrite, this sulfide mineral, it's often commonly found within the ore deposits themselves, you know, be it copper, gold, base metals. It's a common accessory mineral. Sometimes it can be the ore hosting phase, but it's commonly present. But the problem with it is that it's very reactive. So once it collects, or once it's on the waste rock dump, or it's in the tailing storage facility, as you can see here, it will react with air and it will react with water, and it will produce acid and metalliferous drainage. And that's what you're looking at here. Now, this footage is from Western Tasmania. And what you can see is the water is laden in iron. That's what's giving it that red rusty look. But it's got a very low pH. And under very low pH conditions, what we have is the opportunity for toxic metals to go into solution and be transported down the course of that river and impact the riverine communities, inhabiting that particular area. So in fact, all along the length of this river, it's completely and utterly dead in terms of aquatic life until it reaches the harbour that it eventually deposits into. So it's a very serious consequence of poor mine waste management. And I'm just going to take you back down to Tasmania. I'm going to take you to a place called Mount Lyell, and I'm not sure, normally if we were in person, I'd say, how many people here have been to Mount Lyell? And everyone would say, yeah, me. Because if you're driving around the west coast of Tasmania, as many people like to do during their holidays, you take the tour around Tasmania, and if you drive into Queenstown, you will see these massive waste rock piles. So this is what it looked like when it was first mined. So back in the day, it started mining perhaps in the late 1800s. What we had here was more than 20 sulfidic-rich Cambrian volcanic hosted massive sulfide deposits that were being targeted for predominantly copper. I mean, I think they got excited at first and thought it may have been a gold mine, but it's actually copper, which was super valuable too. So much so that there was continual mining activity at this site up until, I guess, the noughties and the teens that just passed. So this is what it used to look like, and this is what it looks like today. Now, Mount Lyell is probably one of the best examples of how not to do mining, because a lot of different things happened over its very long lifetime, over several decades. But what you're looking at here is the moonscape. And this is, if you have been to Tasmania, it's quite famed for the moonscape. So what happened was, back in the day, they were using actually pyrite in the waste materials to drive their smelter. And obviously when you roast pyrite, what you generate is SO2, which then reacts and you generate acid rain. And this led to complete denudation of the hillsides here. Actually, the locals are quite proud of this. There was a PhD study where they went out, they tried to look at revegetation options for the hillsides. But the locals, they were quite proud of their moonscape. So at night they'd go out and they'd rip up all of the vegetation trials the PhD student had put down. And so I think quite soon that the PhD student had to abandon their topic and move on. Regardless of that, though, what you probably have seen while I was sharing that story is some of these features here. So what you're looking at here are some of the slag piles. So these are some of the slag deposits that were associated with the pyritic smelting. But you might just be able to make out some of these rusty orange red rivers here. And that's the acid and metalliferous drainage coming off this site here. So it's a really good case study example of how not to manage mine waste materials. Here we can actually just have a quick video scoot around the site. We can look at some of the major sources of acid drainage in this particular mine site. So what you're looking at here are waste rock piles and some of the denuded vegetation or lack thereof hillsides. And we can see that over the course of its lifetime, there was probably more than 50 million tonnes of waste rock actually dumped around the outside of the mine site. And this waste rock probably contained about 10% pyrite. So when that pyrite is sitting there in these piles, as you can see here, you can see this is ripe for oxidation reactions to occur. And what you're looking at here is some of the acid mine drainage at the foothill of the slag pile. So, other sources of acid drainage, actually within the rock package themselves, the intrinsic rocks, there was actually natural pyrite there. So we have a contribution from the, a background contribution from the natural rock packages, but certainly mining and excavating and putting the waste rocks on the surface has contributed to the AMD. There's also acid mine drainage coming from the underground mine and associated caves areas, but also back in the day, they thought that a really smart way of depositing of the tailings was actually put it straight into the river. So within the whole of the Queen and the King River system, we have more than 85 million tonnes of riverine tailings deposited in there, and some slag materials too. And so when we try and calculate how much acid drainage will be produced from all of these different wastes in this area, ANSTO predicted that acid drainage will continue to naturally be produced for more than 600 years unless we do something about it. So the challenge is on. In terms of chemical pollution, the challenge is there. We've got to do something about that. That's 600 years of AMD that we just can't afford to have anymore. So that's a chemical example. But, I talked to you a little bit about physical examples, and I'm sure many of you must remember this. This only happened 2 years ago. This was, skip past it. This was back in 2019, in fact. This is when I joined UQ, probably about a week before I joined. This tailings storage facility disaster happened in Brazil. And what we're looking at here is the collapse of a tailings wall, and all of the mine tailings that were contained there spilt out into Brazil, into Brumadinho. It killed over 250 people. And, for many, many different reasons, and there've been many inquests and investigations after that, it really shouldn't have happened. And, as an industry, this was really a turning point. This was the point in which the global community, in terms of the miners, the financiers behind mining, they came together and they said, look, we've got to draw a line under this now. We've got to stop this happening, because only a couple of years before that, in 2015, another tailings storage facility had failed in Samarco. And only a year before that, another one had happened in Canada at the Mount Poly site there. So, it's obviously something had to change. So when we come back to the conversation we were having before in terms of the war on waste, I think Craig really missed something in the coverage that he gave to the ABC, and I did email the ABC, and I said, look, I really think you're missing something here, because all of these waste streams you've talked about, and you actually saw some real things happen in terms of plastics. McDonald's, they changed their straws, textiles and foods, kids in classrooms, they were really getting back into kind of thinking about recycling, sustainability. But what about mine waste? And so I guess what we're doing here at UQ, and not just us, but our colleagues at RMIT, at Curtin, at the University of Tasmania, all of these university departments, we have a strong community of people who are focused on actually taking up the mantle and proposing a war on mine waste formally. So, my team here, my Watch team, and here you can see my postdoc Laura Jackson and PhD student Laura Nichols, what we're doing is we're looking at ways in which we can improve how we predict the environmental properties of the mining waste. Can we design that mine better from the outset? Can we think about new tools and techniques to actually better characterize if something's going to form acid or metalliferous drainage? Can we take existing data and run machine learning algorithms over the top of that data to pull out environmental indices that we need, particularly if those data sets already exist? So there's so many things that we could do, and there's so many things that we are doing. Little time to talk about it, I may add, but I'm just going to touch on some of the main things that I think have changed in terms of the global war on mine waste. So firstly, in terms of thinking about stability of tailings dams and what we need to do better, as I said, after Brumadinho happened, the community really pulled together. And what was great to see was that a new tailings management standard was produced. And this is called the Global Industry Standard on Tailings Management. And it was released just last year, in fact. And we had professors from here at UQ involved in this. So Professor Deanna Kemp at the SMI, Professor Daniel Franks, Professor David Williams over in civil engineering, all of the, the global experts that came together, they worked with industry and they produced the global tailings standard. And it comprises of 6 topic areas, 15 principles and 77 auditable requirements. And all of the mining companies are taking this very seriously indeed. So right now, every single company is looking very closely at the standard and thinking about how to integrate it into what they're doing. So this was a really positive step forward. And this is great in terms of the physical stability and trying to prevent things from Brumadinho happening. But I haven't seen something equivalent happening in the space of chemical. Another thing that's really sort of seen some good change happen in terms of waste characterization was the Paris Climate Agreement, because what it really was saying to us in the mine waste space was that we need more critical minerals. And critical minerals or critical metals are really important in Australia, and Australia is really looking at building its critical metals sector, because these are fundamentally the building blocks for many of these new technologies that we need. And this is a great figure here. But many of these new technologies we need for clean energy, they have things like cobalt and indium and lithium. And for people working in mine waste, we know that these are metals that are concentrated in our waste streams. So surely, one of the things that we need to look at, and also rare earths too, but one of the things that we need to look at is thinking about if we can break the pollutant linkage chain in a completely different way. If we actually look at this material as being valuable, we might actually have a shot at economic rehabilitation, because this material we know is very endowed in some of these critical metals that we need. So really mine waste plays an important role when we think about the conversation around circular economy. And we know that in Australia, we want to grow our circular economy business to become, a $26 billion industry by 2025. I don't know if we're going to quite do that. That's a little bit of an old article, but certainly the gauntlet is there. We need to rise to the challenge, and we've got great opportunities to do so. Across Australia, there are so many candidate sites we can go and look at. And obviously I don't have time to talk about all of those, but there are just thousands of sites across Australia. One place where I used to live and work and breathe was Tasmania, which was great. And what you're looking at here is a map from the state government. And this map really shows you where all of the hotspots are in terms of mine waste. But many mining companies down in Tasmania now are really looking at this map in a completely different way. And instead of it being a map for looking at where mine waste is, it's kind of like a target map. Where should I be looking at, the next generation of ore deposits? Because really that's what mine waste is. It's the next generation of ore deposits. If we can remine that waste, we can break that source pathway receptor chain, that pollutant linkage chain. We can stop AMD if we reprocess and pull out some of these metals that we need for our clean energy goals and technologies. So one site I want to take you to is Savage River here, and very quickly, I know I'm running out of time. What we're looking at here is the old tailings dam. And this is an old tailings dam that's been actively producing acid mine drainage for a number of years now. We've got 38 million tonnes of pyretic tailings. And we did a study where we broke them out into different physico-chemical zones here, which is what these zones correlate to. I don't really have time to talk about the study, but essentially what we were doing was we were looking at cover options for the site back at the time. So that was 2014. So we did a bunch of characterization work, but one thing we did was we did some mineral chemistry. When we looked at the mineral chemistry, we were actually looking to see if there was potentially gold, because I guess we were a little bit obsessed with gold at the time. But one thing that really stuck out was that cobalt was really well endowed in the tailings. And so we got a grant to basically go back and study, specifically the mineral chemistry of the pyrite. And we found that it was very well endowed in cobalt indeed. And that wasn't just, that we'd chosen well a few samples in our previous 2014 study. It was actually really well endowed. So we went back and we did a bioleaching trial. So again, I don't have time to talk about it, but there's a link to a paper there. And in fact, our methodology was noted to be quite good by Hatch, and it featured in the landscape review of technologies to reduce or eliminate tailings. What we found was we developed a methodology to pull out the cobalt from the tailings. And if we were just to quickly look at a business case for, is it actually worth undertaking economic rehabilitation? Well, if companies are driven by money, and if we just sort of exclude the capex and the opex for a sec, just in terms of the contained value, we're looking at about 90 million US dollars, which is quite significant, because if you think about it, some of that money can be used to actually help facilitate future rehabilitation at the site. It could pay for itself in many ways. So what we're doing at this site, we're going back and we're going to be doing some more work there. We're going to be refining our methodology in terms of the bioleaching trials that we were doing. And we're going to be drilling deeper. So the material that we looked at in our first studies were quite shallow, actually. We were sort of looking at material in the upper 5 meters, but this is actually a tailing storage facility that goes down to about 60 meters. So we want to check the grade of the cobalt all throughout the OTD. And if we can prove that actually the cobalt grade is high, and that we can recover it economically, then we could really turn around the fate for this site, which is one of the most problematic sites in Tasmania to deal with in terms of acid and metalliferous drainage. And that's something that could roll out across Queensland. And this is the work that we're doing right now with the Queensland state government. And so, up here in Queensland, again, we have a very large, scary number of abandoned mines to play with. And already it's great to see that there are some examples of remining of tailings at the Century Mine and at Mount Carbine too. But with funding from the state government, we've had the really great opportunity to get out and about across the state and actually look at whether or not we can transform some of these existing mine wastes that we have, both at abandoned and historic mines, but also at operational mines too. So we've been doing our work in 3 different streams. Just probably going to talk a little bit about some of the work that we've been doing in stream 1, where basically we've been going out to sites, we've been undertaking an integrated geochemical and mineralogical program to characterize the wastes that are there. And we're talking about a diverse range of wastes: tailings, slag, waste rock, spent heap leach. And we're looking at if we can pull out additional critical metals to help grow the critical mineral sector in the state and obviously nationally, and facilitate the transition to the new technologies we need for clean energy. So I'm just flashing up some of the names of the sites we've been to and some of the target elements we've been looking for. And as you can see, cobalt and indium, which is used in your touchscreen technologies, they all feature there. And we've also had some sites where we've been looking at rare earth elements. And there's some videos at the bottom there which just show you some of the diversity of the sites that we work at. So here we're excavating tailings using a hand auger. Here we're flying over a spent heap leach pile. And here we're looking at a tailing storage facility, which is completely uncapped. And we can see that in the summer, we've got ephemeral salts forming on the surface, which are really important when we think about metal cycling in these particular areas. So we've undertaken a great deal of work, but I'm just going to share with you some of the things about cobalt, because that was one that really popped up in terms of clean energies as something that we really need. So just in that stream 1 line of investigation through just the chemical assaying of the materials, we can see that across the state, it's very varied in terms of the amount of cobalt we've got. So in a recent in a recent sampling campaign, I should say, Capricorn copper, it looks like we've got an average just under 300 ppm parts per million of Capricorn copper. So we have a student here, Lauren Nichols, who's going to be focusing on looking at the geometallurgy of the mine waste at Capricorn copper and how we can upgrade it. Can we float it? Can we concentrate it? Can we bioleach it? Can we recover that value? We've got a PhD student, Kristin Isbell, who's soon to start, and she's looking at heap leach. And heap leach is a real ticking time bomb in terms of waste, mine waste materials. It's, if you've got oxide deposits and you leach those and you recover your cobalt or other metals, in other countries, perhaps gold is something that you recover, but it leaves behind all of these gang phases, and they're quite staggering piles in terms of volume, particularly in South America. So Kristin's going to be looking at if we can actually pull out additional cobalt and copper and gold from some of the heap leach in the state. And we're doing a detailed campaign to look at mineral processing technologies to recover some of the cobalt in some of our other sites, as indicated by these arrows. But we're also thinking about indium in the state too. So we have a new PhD student who's looking at pulling out indium from some of our sites in northeast Queensland. So these are mostly all in the northwest. So there's a lot of activity going on in terms of thinking about how to reprocess. But it's not just us. There's many activities like this going on globally. So in Europe, for example, through the H2020 projects, there's things like the Sultan project and NEMO. And much like us, they're working on trying to crack this problem of turning waste, mine waste, into something valuable. And we have conversations with them, we learn from them, we share. And as a global community, we collaborate. And the companies too are starting to get involved. So BHP, they launched a $10 million tailings circular economy challenge in Chile, and 10 submissions were chosen and partially funded to show a proof of concept. And there's other prizes too from other boards where they're trying to sort of get people interested and thinking about how we can actually valorize our tailings. So I posed the question before, does traditional management work? My personal opinion is our current approach needs to be looked at more closely. I don't think Band-Aids fix bullet holes. And I feel like that's a bit like what the approach is that we're undertaking right now. We need to do better. We need to be smarter. And through many of these funding opportunities and collaborations, both nationally and internationally, we have a chance to actually do things differently. But how do we actually win the war? And I think that there's a few different things that need to happen. We need to take a systems thinking approach. So a lot of these things that I've talked about, they're all interlinked. I mean, climate change, mine waste, even thinking about housing and growing populations, they're all interlinked. I mean, what we're looking at here is Tekla. This is houses made of local clay. This is 3D printing. New houses, low-cost housing. We've got a growing population, people need to live somewhere. But how about we recover the clays from the mine waste and we use that to make these 3D printed houses? I mean, that would be great. And that's the sort of systems thinking we need to be moving towards. We need to undertake cultural change. We need to tell our kids, and this is me in the classroom, unfortunately one of my kids' classes, but we have to talk to kids about the importance. It's not just plastics, it's not just e-waste, it's not just food waste, it's mine waste too, because the footprint of mine waste is staggering and it's only going to grow. We need to design for closure, and I've heard some mining companies say this. They don't want to think about closing a mine and just having to manage it in perpetuity, which is what they'll have to do if they create something like acid and metalliferous drainage, or if they're maintaining a tailing storage dam. We need to design for closure. So that thing I was showing you with the hyperspectral mineralogy, we need to be thinking like that, but we need to be doing it smarter, better, faster. Those algorithms need to be rolled out much quicker. We developed a Python algorithm and we could only process 1 meter of core an hour. But, you saw how much was scanned there, 35% of that 190,000. So we need to be using our technologies and tools much better to help us do that. And to embrace opportunities to innovate. So I think as researchers, that's something we do, but maybe we need to be better at telling mining companies or convincing them that they need to embrace those opportunities. They shouldn't just be fast followers. They need to be actually the people who get stuck in immediately. But really what we also need to see is global change in practices and legislation. So, I mean, the introduction of the global tailing standard for stability of dams was great, but we need to see that conversation extend much more into management of acid and metalliferous drainage. And I was really pleased to see this this morning, or to switch on my news, from the G7 summit. One of the things that was pledge was to protect our planet. And they made this pledge to conserve or protect at least 30% of our land and oceans by 2030. And they said, we acknowledge our duty to safeguard the planet for future generations. And I hope that's not just lip service. And I hope that does extend beyond the conventional and into, I guess, the slightly more unconventional. I'm thinking about mine waste because it's too big a problem now. As the person said, it's like where carbon was 5 years ago. So anyway, I'm conscious that I overran time. I'm really sorry. But I do want to say thank you for listening. And I want to say a special thank you to my team and lots of other people that I've met along the way. So thanks, Joel. Thank you very much. And if there's time for a couple of questions, that'd be great.
Thank you so much, Anita, for raising an issue that is, as you say, been hidden perhaps compared to some of the big ticket items like plastic straws and plastic bags. So that was a really insightful talk for a BrisScience audience. And I know we have lots of questions. There's a chance to post a few more, just while I let you know that next month we are, as I said, back in person. It's very exciting. I got my vaccine today, so I think by next month we're all going to be well on track. So we're going to be back at the Edge, and we have a very special guest, the Australian University Teacher of the Year, Associate Professor Jack Wang. So that's going to be on the 5th of July. It will be ticketed, but you will need to register as quickly as possible, and there'll be allocated seating. So make sure you sign up to our mailing lists or websites or Twitter and so forth, and we will give you all the details very soon. All right, Anita, I'm going to kick off with just a few questions. So the first one is from Emily, who asks, what do you think about using resource recovery to capture metals from e-waste and recycle it to reduce the pressure on mining? Is it feasible in the future to use only recycled metals for future electronics demand?
It's a great question. I don't think it will meet all of our needs. I think we still will need primary mining. But certainly, and it's with mine waste too. I mean, we couldn't just rely on mine waste for the sources of the future metals that we need. Straight out, it can only supplement our future needs. But yeah, certainly I know there's a lot of great work going on in the space of e-waste and recovery of metals. I mean, I've seen that video that Apple put out with Liam. It's bot that sort of takes apart an iPhone in like less than a minute or something crazy like that. But yeah, certainly recovering our metals from e-waste will help supplement our needs, but it won't fully meet them. Yeah.
Are any of those techniques transferable to mining e-waste now, or is it a very different skill set?
Do you mean remining?
I think this resource recovery for capturing metals from that e-waste, are these very different? I think people often think about there's just this landfill with e-waste in it.
Yeah. Well, I mean, in many ways, actually, there's some really great similarities. I mean, what both need is great sorting technologies. And, when we're, our project at Mount Carbine, for example, that space where we've been working with Tomra, and Tomra also make the sorters for, if you take your plastics down to get your 10 cents per bottle, Tomra, they make all sorts of ore sorting machines, and they're the same things that are used for resource recovery. So there's a lot of synergies in terms of the technologies to support valorization from both sectors. So I think there's good crossovers there. Yeah.
Brilliant. Thank you. And thank you, Emily, for the question. Kevin asks, what about the waste products from the reprocessing of mine waste? What does that waste look like and the environmental impacts? So.
Yeah, no, I love that question because that is completely a great one. I think that last point I made there with the Tekla and reusing the clays, for example. So the clays wouldn't be something that we would recover. There's not typically metal value in there. So they will be the future waste material from remining the waste. But if we could actually 3D print that, then into a house or some sort of usable aggregate, then that would be great. I think one of my favorite ones is thinking about natural makeups, mica makeups. So mine waste is micaceous for some deposits. If you're talking about granites or sort of systems like that, there'll be a lot of mica in that waste. But people want to move away from very harsh chemical makeups to more natural makeups, but then people have that guilt that actually to make a mineral makeup you have to mine micas, but in fact if you can recover that mica from the waste then you could actually valorize it. So there's lots of clever things you could do. And just one last one which I really love is I took you to Tasmania though. I took you to the west coast and I took you to Haulage Creek and sort of showed you that stream from Mount Lyell, But we had a PhD student who was looking at making art pigments from that. So she was taking the iron oxides, she was putting through a detoxification process, and she was roasting them at different temperatures so she could actually make a range of different color pigments, because pigments for art normally come from China, but actually the amount coming out of China right now is in decline. So we're needing sort of a secondary source to actually meet the global demand. And that could actually be a really clever one, because that would be some of the material that's left over from those sludges, which are quite hard to treat. So there's, yeah, I mean, this last thing here, this slide here, waste as a design for it really is. So I think this whole thing around materials science and engineering and working with geologists, I think that's a really great collaboration to see, to think about what we can do with our gang.
Wonderful. Last question is, what's next for you? You know, if you got a large research grant, you know, unlimited funding, unlimited people, what would be on your hit list? What's your big project?
Yeah, that's a big question. So actually, we do have one. We have a project proposal in with a group called AMIRA. I guess they're an organisation that bring together the industry and the researchers. And what we're trying to do is basically, you know, we've got all of these new tools and techniques and methodologies, from characterising the deposit to thinking about, you know, the decision-making tools that sit underneath it. This project we're actually calling Retail. You know, it's 5 modules and 3 cross-cutting themes. But what we're trying to do is we're trying to use all of the things that we've learned at UQ and sort of beyond with some of our national collaborators, and think about how we can actually handle our waste better. You know, we're looking to move towards that zero waste kind of system. And so that's through better characterization, that's through better processing. You know, why are you putting gang material through a mill, for example? We should screen that out better. We should use our sorting and our screening techniques to make sure that we're not wasting energy and resources on processing something that we know is waste. In terms of recovering minerals that are actually already in our wastes, you know, typically tailings, they can be very coarse or very fine. So we need new technologies to actually deal with those two problem ends of the elephant curve, as we call it. So really, it's just this one-stop shop where we can actually just work towards basically the zero waste mine. Because as I said, you know, we can't, the problem is what we do with mine waste. The solution isn't to stop mining, it's just to mine smarter. And, you know, one thing that I would love to do is in situ bioleaching. Why even mine it? Let's just do precision mining. Let's do it in situ. But, you know, that opens a whole other can of worms in terms of fracture networks and pumping fluids in and what might happen there and impacts on aquifers. So there's a lot to do, but certainly I think we're making good steps towards doing it. Yeah, and I would love to see the legislation change. If I could also just casually influence government and just be like, hey, you actually do need to just regulate a bit smarter. That would be great. Yeah.
Well, that's some fantastic notes, both inspiring and also a call to action for everyone. So, you know, keep an eye on your next legislative agenda coming up in case Anita's got an item in there.
If there's one last thing I would love to say, and I don't know if everyone can do it, but perhaps when everyone's out and about, sort of on their next holiday, once they're allowed to travel again, if everyone can just take some pictures of mine waste and just tag me in them. I think if we just actually all just make a bit more of an effort to just go out and just document what's there, I think this public pressure will actually help drive the conversation. Because what Craig did with some of the other waste streams was fantastic. So I think just something like that would be great.
Great. Hashtag. What's your handle on Twitter?
It's
Twitter, Insta, or
Fox down there. But also,
yeah, of course.
Maybe everyone should just put hashtag war on mine waste. That'd be great.
And hashtag BrisScience too, and maybe we'll have a great montage for your follow-up BrisScience presentation in a few years when we see some of these new technologies coming through.
Yeah, that'd be great.
Well, thank you so much for your time this evening, Anita. I really appreciate it, and a fantastic talk and so many great questions. Sorry I didn't get to everyone's. There's still more coming in now around getting students involved in renewable energy. So save them up for next time, or maybe engage on Twitter still to come. But thank you much. And if everybody stick around just after the end of the presentation, there will be a little pop-up survey. We'd love to get a bit more feedback from you. Otherwise, we'll see you all in person next month. And of course, we'll be on YouTube very soon after this if you need to catch up. Thank you all and have a great night.